Buenos dias. Good morning. We are going to present today a concept called digital twin for processing low-grade ores. My name is Osvaldo Bascour. I'm the principal for OSB Digital in Houston, Texas, and I work also with SIC, which is a company that provides advanced analytics. We're going to start with an agenda showing some of the common pains that we have in these production processes with low-grade ores. And we are going to see how the process integration using digital twin to maximize the metal production, the tons per hours, and the water recovery becomes a very interesting synergy because both has to be compliant for the maximization of the production of copper and molybdenum. We're going to look at how these predictive models, which are hybrid based on process engineering and data, to support better dynamic decisions. We're going to show a case and several other cases and draw some conclusions. The key thing here in low-grade ores is the drastic increase in energy and water cost or water usage for sustainability. When we go from 1% copper to 0.5% copper, we need to mine a lot more rock that needs to be that is using the energy and is also using a lot of water. So we have to manage this process integration completely different on how we have been used to with the traditional other operation with higher grades, which require a different approach. One of the things that we find that is very interesting is that management is not receiving the right information at the time to make the best decisions. We also see that we have too many spreadsheets running around that doesn't allow for everybody to work together in a systematic process to look at the whole chain supply, to provide the right KPIs and each step that all are synchronized correctly to debottleneck the plant at all times. What we need for these processes to improve the production rate and the water recovery, one of the things that we need to understand is that we need to reduce the stability of the grinding process from the traditional and reduce this variability and avoid at all times some rheological constraint for mill overload, hydrocyclone roping, and low, because they cause low water recovery. The particle size distribution is what enables to get the right flocculation, as we are going to see. And of course, the grind cut that we need is based upon the grind cut and the distribution, because if we have too many fines, the flocculation doesn't work and we don't have the right amount of water that needs to be reprocessed in the plant. So the production of copper is completely tied with the production of copper in these new low-grade ores. So here we are showing the metal production and the throughput. Both are related here in this curve. These curves are changing in real time, so any simulation that you might use does not work because the grades are changing and the ore variability is changing. So we need to detect those in real time. So the first thing that we do is that we need to organize all the data in a digital twin and then identify what are the hidden losses and how much those are costing to tackle every opportunity in the right direction. Then we can use information that is created from the events and the data to create the modeling that is required to predict and avoid the constraint and then move towards the deployment and the usability for everybody to get on board. This requires a process for implementation. There is some consulting, some advice, and the training of the people so they get used to this new way of working. The key thing is to have a clear goal, in this case, maximize the copper, reduce the water consumption, increase the water recovery and decrease the specific energy consumption. So what we have found is that people looked only at the flotation and the copper recovery, but they don't include the water. And the water is something very, very important, as you can see here, because this water has to go back to the grinding to get the right size distribution. And this has not been accounted in the past. So when we started to look at this, we looked at the maximization of the copper by looking at the maximum tonnage, the grade that is coming from the mine, and the recovery that is obtained in the rougher section of the plant. But we found that today, to run this mill correctly, we need to have the right amount of water. So we have the increased throughput with the increased amount of water which is required for grinding flotation. So we have to look at this integrated rock and water processing management today, where we got the plant from one side that has to provide the right size distribution for the flotation and for the water separation. Otherwise, flocculation doesn't work and we lose a lot of particles into the tailing ponds. In this case, we have a coarse tailing pond and a fine tailing pond, and all that are creating the water that comes back to the plant, and we need to manage the rheology in the mills, sack mill, ball mills, and cyclones to get the right size distribution for the maximum recovery of water and copper. So this has been a very interesting project where we have a database that enables us to capture that water and to return the water, the adequate amount of water for maximizing the transportation of the pulp through the process and the maximization of copper in the flotation cell by looking at the hydrodynamics of every flotation cell in the process. So what we do is that we use a digital twin. And what is this digital twin? It's an abstraction of all the processes in the plant which enable us to follow the pulp and the flotation of the metal and the recovery of water sufficient enough to get the right grinding, and we are going to see some very interesting results as we go. And we build a database that contains, for every unit, we are looking at the events, we are collecting all the data, and the events and data are transformed into information so we can look at improving the rock processing, getting the right amount of water, and the mineral processing site in a very well organized and integrated process. This has to be run like a switch watch. We cannot be having this into a processing of the ore and processing of the water. They have to be all integrated, as you see in this diagram that I have presented here, because the amount of water that we got here is very, very interesting, and there is no places to put the tails. It's very tight. It's a different world here when we start dealing with low-grade ores. So an important thing here that I wanted to stress is that data that is captured requires events. And the events, which are the operational events, has to be captured and characterized to get the right context, to have the right information, to draw the insights, to move closer to the constraint, and to maximize the copper production without violating the rheology constraint, hydrodynamic constraint in flotation, and the hydrodynamic constraint in thickening. So for that, we use this software called SIC, which runs in the cloud and enables to do the analysis and transformation of the data into information to create the models and to share that analysis, which are running in real time with management and with the whole plant, so they can work together, so they improve the decision making. And we can also use Python in this environment, Jupyter, that is included. Now that we got information, we can use any kind of new tools that are available in the market to analyze the data. Here we are showing how we are classifying the data with the different capsules or events and detecting where we have losses, which is the first step. That once you have the database created, this is the first step where you start identifying the losses of money by events which are negative to the production and to the recovery of water, and also the equipment downtown operating, trouble times, idle times, and those characterizations, which are all represented here, enable us to have a good set of data to predict what's going on in the plant so we can avoid uh, having problems. So one of the first things that we do is that we take the grinding system from the stockpile and we do the sack milling. We try to maintain the right distribution of solids that goes into the sack mill. So we have the right grind here. We add the right amount of water. And as you can see here, this number here becomes very important, the amount of water that we add into this tank. So we have the right percent solid going out into the cyclones and obtain the right amount of distribution, which is characterized by the M of the Godin-Schumann distribution, which we are calculating in real time. The percent solid, which is the production to the flotation, that has to be very well statistically controlled so we don't have disturbances into the flotation. So we are managing here also the size distribution, which affects the flotation. As we know, the fine particles don't float very well, the coarse particles don't float too well, so we have a range of particle size that we need to have the right flotation, and this affects also the flocculation, so we need to have the perfect size distribution for both flotation and the water, which is required here to add to the mill for the right rheology, so we don't have the overgrinding that is happening sometimes in these very tight operations, sack mill and ball mill. So the rheology is the controlling factor, and what we have found here is that the cyclones are the bottleneck. So to manage that, we need to manage very carefully the particle size distribution, and we have to model it in real time so we know the effects and how to control it and to learn about it as much as we can. So we have a very nice online model based upon all the key variables, and there we know and we characterize which are the manipulated variables which enable us to control the right variables to avoid violating the costly process constraint and to reduce the variability of the grinding product going to flotation and to thickening. So in flotation, now that we got the right particle size distribution and feed, we try to maximize the net metal production in the flotation cell by calculating that, cleansing the data, and having that available. What we have done also is to provide the right bank profile of hydrodynamics for every cell. So we are calculating the hair holdup, which is based upon the Kolmogorov number, power divided by the volume of the cell, the air velocity, and the froth. That number that has been published and discussed in other papers is very important to find the right profile, which provide us in here, as you can see, a gain of 6 tons per hour, that if you do the multiplication is millions of dollars savings when you do this with the right switch watch approach. And then we have a way to better manage every element following the gain and losses, and we maximize the throughput of metal production by having the right amount of water. That we have been found that is the critical part of this implementation. So we go from 15 tons per hour to 22 tons per hour of copper. Another thing that we find when we are looking at optimizing this is that we need to find what is the maximum, what are the constraints, so we can stay outside the constraint. When we did this, we look at the historical data, and we found that the optimal is obtained about 4,300 tons per hour, and we cannot get to the 47 because number one, we don't have enough water, and second, the cyclone start roping and causing over grinding, which affects both the flotation and the thickening, as you are going to see. So we found that about 200 microns is a reasonable particle cut, and also 68% solid. The maximum amount of solids in the cyclone usually is about 65 to 68. This is pushing, but the most important thing is that we are following the copper production. And that tells us where we need to be, because we want to be at the maximum level in real time at all times. What we have found too, this is some research that we did many years ago, and we find that if you are over 77% in the mill, for instance, you are going to have a paste, and this paste has the material gets ground too fine, and that fine material affects, because you create a bimodal size distribution which affects the rheology of the pulp. And we do have models which we have developed over the years, which are running in real time as pseudo viscosity analyzers, sensor, which enable us to avoid these constraints, which is the most important part of this whole process. Here we see that if we maintain the right size distributions, we get an increase of water recovery of 42%, because we can encapsulate more solids, and we go from 55% solid to 60% solid, removing more water. As you can see here, the flow of water coming out of the cyclone, excuse me, of the thickeners and of the cyclones here, because we got the coarse material and the fine material. Um, this is very clear how this improvement is obtained just by looking at the overall set of data. So consistently here, the right size distribution help us with both water recovery and the copper production rate. This is an example using SIX, which is a very vital tool to, I mean, there's many things that I could show here, but this is one of them that is showing the effect of the size distribution that we are managing with the Godin-Schumann distribution, because it's very easy to calculate. And we can find that here most of the time where we get about, as you can see here, 5,500 tons or close to 6,000 tons per hour of water are when we maintain the right size distribution. Otherwise, the water doesn't get it goes down to the drain. Let's put it that way, and it goes to the tailing ponds, and it's very hard to recover water in the tailing pond rather than doing it in the thickeners. And so the integration of both the plant and the water enable us to manage the plant to the optimal characteristics of the ore by getting the right rheology, getting the right flotation, the right hydrodynamic profile that does the maximization of the copper, and we get the right amount of water back into the plant to get the right water rheology and water distribution in the plant in real time. If we don't run this correctly, we have roping on the cyclones, and the mills start producing too many fines. How this one is implemented, we take the data from the process control system. It goes to this digital twin, which is a database running in this case in Pi system, and we use the SIC Advanced Analytic to do the analysis, to create the online analysis that is distributed and can be done on a daily basis. You don't have to be repurposing. You can repurpose this analysis all the time, and we also use Power BI for further analysis and presentation and analysis of different cases to eliminate any hidden losses by coming up with the right decisions that are sent back as suggestion to engineering and to operation for them to implement. So we get rid of this red flotation and thickening, so we get the right amount of grinding product that gets this flotation and thickening into. So it's very important to have this coaching and look at this remotely. We are using the cloud to create real-time dashboards, so we can put this into the hands of the real people, and they can use it either locally or anywhere they are. These are all running in the cloud. We improve the process fluidity, so the people from operations can look at this. They have in the control room, and in many places they have, in the cloud, they can look at the data and they can optimize the yield, performance, reduce operating costs and failures. And based on your environment, they can define optimal production rate for your plant. And the key thing is that you enable people to do these things on their own by having the right database and be able to explore, analyze, and make the right decisions and reduce the time for better decision, improve communication between the teams, engage subject matter expert, and elevate the team knowledge. So in general, this digital twin plan uh, transform the real-time data into information by the user at the desired degree of detail so they can come up with the right models to understand and to increase the visibility of the unknown and to pass that on to operations, engineering to do their calculation for better dynamic decision support of the mining complex. So the targets are better defined and obtained, and also the execution is better analyzed to improve when it's required to increase the production by 30% in one case and water recovery by 40 case, enabling both to be maximum when we do the right grinding. Uh, by system and seek as many synergies in a practical way as we have detected and put into practice for this case. We improve the operational efficiency and sustainability for lower group costs. People is very important concept, and there is a tremendous change in the process business integration. The workflows start changing, so it takes time to get these new technologies into up to speed. It's not immediate. There are some other companies that have been using some of the same strategies, like ArcelorMittal, Anglo American, Barrick, and in this case, Lumina, with this much advanced, I would say, advanced data analytics. It makes the result come up much faster than ever. So if you have any questions, please let us know. Here is my email and phone number, and I'll be glad to answer any questions if you have. Thank you very much.